So unfortunately, I didn't record the derivation of the non-inverting case. However, I made up notes for the non-inverting and the inverting case and made notes of them and did a video that already exists. I did it this morning. All right. So if you're wondering where half the lecture went to, I forgot. Now, yeah, if you don't see me press record, you could certainly tell me. But I don't blame you. I blame me. So before, for the inverting case, it was really, for the non-inverting case, it was really kind of easy. It was 1 plus R2 over R1, omega naught, S plus omega naught, and omega naught equal 2 pi beta gain bandwidth. Okay. And you can use nodal analysis with this as well. And you would just put V out equals 2 pi gain bandwidth divided by S, V plus minus V minus. And you could do it that way. But going around that way, and you'll get algebraically correct answers, but by doing it the system way, you'll get a model that you should be more familiar with. And the only pain that we have to do is a little bit of superposition. All right, so let's do some superposition. So I'm going to put the summer back here. All right, and I have plus and minus, and the op amp transfer function is going to be 2 pi gain bandwidth divided by S. That's going to go to V out, and then we're going to have some feedback, right? Now the thing is wait, how, before it was easy because N was at ground and I just did a voltage division. Well, let's do a superposition. That makes N at ground, and then we're right back to beta equals R1 plus R2. All right, I'm gonna just rewrite that a little better. R1 divided by R1 plus R2. Now, before, in the inverting, non-inverting case, we just brought V in. But now it's actually coming in on a different pin, and there's a resistor in between. Again, that's easy. So we know it's going to be altered somehow. And how will that be altered? Well, now we short V out, and we have voltage division the other way, and we call it alpha R2, R1 plus R2. Now you might be saying, hey, it's going on the negative pin, it should be subtracting. And you're right, it should. But to keep the same flow, if you will, I'm going to put the minus sign here and have it still be added there. I tried it more than one way, and keeping it that way seemed to come up with something more clean. All right. V out equals, now, what's V out? Before it was just V in times this function. Now it's V in times alpha, which is this, times 2 pi gain bandwidth, right, divided by S, minus V out beta 2 pi gain bandwidth divided by S. V out 1 plus all right. Now, maybe you think I'm making a big deal about, hey, this is negative feedback that turns into a positive. It's just I've gotten the question a lot over the years. And yeah, sometimes on exams, I see a lot of misunderstanding on midterm 2. People tend to get it by the final exam, but I just thought, why not make our lives easier? So QS is going to be V out over V in, right? Alpha 2 pi gain bandwidth divided by S. All right. So let's multiply the S through, and we're going to get alpha 2 pi gain bandwidth S plus 2 pi beta, right? Because the S's will cancel. Now, I had mentioned it before, but when will this act like an ideal op amp, right? Well, before it was 2 pi beta open loop gain was greater than 1, but now this S changes with frequency. So this term has to be bigger than that term. And in the past, sometimes I would just say, oh, 2 pi beta gain bandwidth has to be greater than S. Well, that's not exactly true, right? Because S is a complex value. So really, we have to put the magnitude symbol around it. So, and it really is not just greater than, but it's much, much greater than. So if this is true, right, then this will behave like an ideal op amp. And let's just, work it out. If 2 pi beta gain bandwidth is bigger than, well, S is j omega, right? So finding the magnitude of that is the square root of omega squared. There's no real part. And so really, it just has to be bigger than omega, or canceling out the 2 pi's, which is interesting because that was the same result that we got for the non-inverting case, right? Because in fact, the feedback this part was the same as the non-inverting case. This part was the same as the non-inverting case. The only thing that's changed is that the input is inverted and scaled. So I have a constant divided by S plus another constant. First order low pass. Omega naught is still 2 pi beta gain bandwidth. Now, this still isn't in a form, I think, that, is like kind of easy to see. But remember, 2 pi gain bandwidth equals omega naught divided by beta, right? Because this is omega naught, it's got 2 pi, that has 2 pi. That has gain bandwidth, that has gain bandwidth. This has beta, this doesn't. Oh, okay, well, we'll make them the same by dividing through by beta. So now I have alpha divided by beta. Now I'm going to put in my omega naught, S plus omega naught. Well, what was alpha? That was minus R2, R1 plus R2. What was beta? Oh, beta was R1, R1 plus R2. All right, well, these cancel. Minus R2, R1, omega naught, S plus omega naught. And yeah, I should have put the omega naught in there to make it mathematically proper. Wow. So why do I like this form? Because this I would remember from my 98 days, and this I would remember from my 110 days, 2 weeks ago. Combine them, and now you just have a low pass filter, right? Not one that you would use to actually filter anything, because gain bandwidth will vary quite a bit from chip to chip, right? It's not anything you can necessarily design with, although you might say you could hack your system, right? But yeah, I got a low pass filter with an op amp and 2 resistors, and I didn't need the capacitor. Okay, you can do that. But so let's do a Bodhi plot of that. I'm going to keep it in frequency this time. I'm going to call that. So the gain bandwidth, if I recall, was 10 meg, and now I'm going to go over 3. 1, 2, 3. All right, so my model, right, of gain bandwidth, all right, 2 pi gain bandwidth divided by S, but if I take the magnitude of that, I can convert that into gain bandwidth divided by frequency. So I go over 10, up 20, up another 20. This doesn't look right. Oh. I guess I messed it up already. 1, 2, 3. 1, 2, 3. So 20, no, 20, 60. Now, we haven't talked about phase yet, okay? But let's just concentrate on the magnitude part for right now. Well, here's the thing, right? To convert to dB, you take 20 log, right? Right, you're finding the magnitude. So that minus sign goes away, and you really just get whatever the positive dB, and you get a phase of minus 180 because of the negative sign. All right. So if R1 and R2 were equal, right, I'd have 0, right? And yeah, simplification, you can bring it right out to here and bring it down. I'm going to show you that it's not exactly that simple, but for the homework, you really can get away with that. Well, what if the gain was 20? Okay. You bring it here and go down. What if it's 40? You bring it here and go down. And what if it's 60? All right. Now the thing is each one of these is the minus 3 dB point and the minus 45 degree point, right? These are all FCs depending on whatever beta happens to be. All right. So if our gain was 60, right, that's minus R2 over R1, but beta is R1 divided by the sum of the resistances, which then gives us a new cutoff frequency, right? So here's the thing. If I'm going to do the phase, now this is the kind of the annoying part. This minus sign, right, means to me minus 180 degrees of phase right off the bat because it's inverted. So I would put minus 180 degrees. Then, so that's 10K, that's 1K. So I would come up, right? Then I would go through the minus 45 part. So minus 180, minus another 45, so that's 5, minus 135, right? Then I would add another 45, so minus 180 minus 90 is minus 270, so that's 10 times this FC, right? And I'm just going to put this is the one we're talking about, right? So then that comes here and goes there. All right. Now, if the gain was 40, the cutoff frequency would be here, and you would get this curve shifted over. If it was here, you get that curve shifted over. All right. Now I'm going to see if I can go back and do the phase up here. Okay. So this is the minus 3 dB point, and it's also the minus 45 degrees point, right? So this would be if the cutoff frequency was 10 kilohertz. All right. So for the phase, because it's non-inverting, the gain doesn't have a phase, doesn't have an automatic phase to it. So it starts at 0, just like a normal low-pass filter, right? It stays 0 until 1/10 of the cutoff, right? Then minus 45 at the cutoff, and then minus 90 for 10 times the cutoff. And that would be the phase. And if it were 100K, this curve would be shifted out. If it was 1 meg, it'd be shifted out. If it was here, it would be shifted out. Okay. Now this is all for this simple model here. All right. Meaning 2 pi gain bandwidth divided by S, right? It's all for that simple model. Now the thing is why is it so powerful? Is because if I add this, well, that's 1 hertz, and we're talking, and really it doesn't matter at the DC end as long as it's bigger than what you need. The fact that it's not an ideal integrator model doesn't matter. That open loop gain is still a lot bigger than whatever it is you're setting your circuit gain to. So it effectively drops out. But then sometimes okay, sometimes you have really more than one pole, right? But let's say this is 1 and this is 10. Well, let's just say 1 megahertz, right? So, and let's say 1 gig is out here, right? All that would do is that, right? So here's our 0 dB point anyway. So this is where we were designing anyway. So yeah, that's so big, right, that we can sometimes safely ignore it, okay? Because it's just so far away from our region of interest. And in fact, right, what would the inverse Laplace of that be? You have e to the minus s for the 1, you know, plus or you'd have one, and I forget, right? Plus or minus this, plus or minus e to the minus 1 gig. No, time. Oh, I'm sorry. Time. So this decays so fast that really you're mostly left with a first order system. That's why that model's so powerful. But there's trouble, and I'll tell you. And it can come from the simplest of circuits. Listen, I have some notes. Why do op amps ring? Okay, so the thing is what is ringing, right? That's a ring, right? That means it's underdamped. So if I have a step function coming in and I get a ring, well, then I have underdamped, and it means two poles. Now I'm just going to rewrite one of the previous examples down, 1 plus R2 over R1 omega naught S plus omega naught. This mathematical model cannot ring because there's only one pole, right? So even though I said as long as you're kind of far away from that region, it should be okay, some days it's not okay, all right? But this model won't work, right? Because we talked about kind of like an AV over S, simple integrator model explains a lot that what happens. Then we even did, you know, a little bit better is AV S plus 1 or some number, right? A little bit better, but still only one pole. So how do we get two poles? Well, I'll tell you. So I can kind of just come up with an example where the open loop gain as a function of, I think I'll put a mega here instead of frequency, right? Is that I can have two poles. All right. 1 radian per second, 10 gig radians per second. All right. I can have this and to make the model work right, if I want this open loop gain to be the gain at DC, then I set S equal to 0. 1 times 10 gig gives me 10. So I won't get that if I'm dividing AV divided by 10G. So I just put it there. That's where that comes from. All right. But now we have a two-pole model. But hey, is this over, under, or critical? Under, right? Because, yeah, two real poles. But remember, when we use feedback, we can actually get a change. So here's this buffer. Let's do the model. H of S equals all of that. Okay. Vn. Okay. Now notice, there's no resistors here. V out equals V minus, and so there's no beta, or beta equals 1. All right, so it can be shown that the new transfer function is this, right? Because it's always of the same form, right? You have HS divided by 1 plus HS GS, right? HS in this case was AV 10 gig, S plus 1, S plus 10G, all right? And GS, right, we've just said is 1. So I can go through all of that, by identifying that, I can just use that form almost right off the top of my head. Now, we don't necessarily care about the numerator because it's really the poles that's giving us the action. Well, these are real, but notice it's not the whole picture, right? S times S, S squared. 1 times that is 10G plus AV, and then you have 10G plus 1, right? Now here's the thing, right? 10 gig plus 1, you can't write that number. So I tend to know that I haven't forgotten about the 1, right? I just put 10G plus 1, right? That's the best way I can approximate it, all right? Well, now, where are the roots? Well, minus B plus or minus B squared minus 4AC divided by 2A. This part here is going to tell me over under critical. So B equals 10G plus 1, right? B squared equals 10G plus 1 squared, and 4AC equals 4. A is 1. C is, there's no S term over here, is 10G plus AV. Where now as before, hey, those were 2 real roots. But now I have added this gain term. And the bigger it is, right, the bigger this open loop gain term, right, the chances of this being bigger than that go up, and you're going to see ringing. All right? Now, where is this a buffer? All right? So I'm going to go back to this, or I had S plus 1, S plus 10G plus AV. Oh. No. No, I was right the first time. So in order for this to act like a buffer, right, really, one way to look at it is just AV just has to be bigger than the magnitude of that, okay? And that's really all you got to say in the homework, all right? And that when that occurs, right, it'll act like a buffer, okay? That's all. We're out of time, unfortunately. Yeah, I guess the difference is this has a real and an imaginary part, and I think like if you were to like really calculate this out, it would probably be when AV plus 10 gig was greater than the imaginary parts, and then it would cancel out better, right? Yeah. Anyway, that's just a thought. And yeah, I guess what it is when you're dealing with the second order model, in general, you're just trying to find out, is this circuit going to ring or not on me? Okay, I guess that's it for today. Okay, I don't see any questions. Okay.